Hello and welcome to our last section video for chapter 37, where we are going to discuss the endocrine glands in section 5. Our learning objectives are to describe the role of different glands in the endocrine system and explain how the different glands work together to maintain homeostasis. So a lot of this is going to be review from the previous sections, but again, it's a good way to kind of summarize and fill in any knowledge gaps that we have. But before we get into the different endocrine glands, we're going to compare the two control systems of the body. So we've been talking about our endocrine system, and we've already studied our nervous system, and both of these are going to work to coordinate and integrate the activity of our body cells. There are some differences though. Our endocrine system is going to be slow because we have to secrete that hormone. It has to travel through the blood, make its way to another endocrine organ, and then maybe release another hormone. It takes time. Whereas with our nervous system, we are going to send impulses very rapidly. And because we send it rapidly, we get a rapid response, but it is short-lived. Whereas in our endocrine system, we are going to take our time releasing those hormones and getting them to the target cells, but we get a longer response that can last from minutes to days or weeks, depending on what type of mechanism we're talking about. And then we've talked about how hormones travel through the blood. We classify hormones as ligands, which are just chemical messengers, whereas we're going to utilize nerve impulses through nerves in our nervous system. Now let's talk about our hypothalamic pituitary axis. So essentially this is the communication that takes place between our hypothalamus and the pituitary gland. We know that our hypothalamus will hormonally stimulate the anterior pituitary gland so that we can release hormones. And these hormones that the hypothalamus is going to produce are called regulatory hormones. And they travel through an area known as the portal system here. Our portal system is basically set up by two capillary beds with a vein connecting them in the middle. And in this fashion, the hypothalamus will secrete some releasing hormones, which should increase release of hormones from the anterior pituitary gland. So for instance, we were recently talking about the thyroid gland, and the hormone we said was released from the hypothalamus was our thyrotropin releasing hormone. The hypothalamus can also synthesize or make some inhibiting hormones, and this decreases the stimulation or secretion of anterior pituitary hormones. So for instance, most of us are secreting prolactin inhibiting hormone, also known as dopamine, so that our anterior pituitary gland does not make prolactin. And once our anterior pituitary gland decides to secrete hormones in response to these regulatory hormones from the hypothalamus, it puts them into our blood circulation so the hormones can travel to where they need to go. So if you haven't gathered by now, our hypothalamus really controls the pituitary gland. And we know that the pituitary gland is named the master gland because it pretty much controls a majority of the other endocrine organs within our body. Another name for our pituitary gland is the hypophysis, and we see that it lies just inferior to the hypothalamus in a bony area that is known as the sella turcica, which means Turkish saddle, and it's a part of the sphenoid bone in our cranium. We'll talk more about that in A&P. And it's quite small even though it does so many things. It's about the size of a pea, and it connects over to the hypothalamus through a infundibulum, or we can call this the stalk of the pituitary gland. And we've already mentioned it's divided into an anterior and posterior pituitary gland. So let's talk about the two different parts of the pituitary gland some more. The anterior pituitary gland is also called the adenohypophysis. Adeno means like glandular, so we have a lot of glandular tissue in here. And like we said, we communicate between the hypothalamus and the anterior pituitary gland using a portal system, and the fancy name we give to that is our hypothalamo-hypophyseal portal system. The primary plexus up here is a porous capillary network and is more associated with the hypothalamus, whereas the secondary plexus down here in the anterior pituitary gland is associated with the anterior pituitary gland. And then we have the hypophyseal portal veins in between that allows them to transport the hormones down. Now let's review some of the hormones that are released from the anterior pituitary gland. First, we have our thyrotropin stimulating hormone, or it's simply called your thyroid stimulating hormone. And this travels over to our thyroid gland so that we can secrete the thyroid hormones from it. Next, we have prolactin that's released, and this is triggered by our prolactin, and we have all the names listed here. It's stimulated by our prolactin releasing hormone, and we have our prolactin inhibiting hormone. So if the stimulating hormone is released from the hypothalamus, then we produce prolactin and it travels to the mammary glands so that we can cause milk production and mammary gland growth in females. Next, we have our adrenocorticotropic hormone, or ACTH, and this is triggered by the corticotropin releasing hormone in the hypothalamus that travels down to the anterior pituitary gland and over to the adrenal cortex so that we can release corticosteroids. Next, we have our gonadotropins. So the hypothalamus is going to secrete our gonadotropin releasing hormone that travels down to the anterior pituitary gland and tells it to synthesize and secrete the follicle stimulating hormone and luteinizing hormone. And in the female, it'll help regulate ovarian development and secretion of estrogen and progesterone. And in the male, we will see sperm development and secretion of testosterone. Then lastly, we have our growth hormone, also known as somatotropin. And we are going to see that our growth hormone releasing hormone is going to secrete from the hypothalamus, goes to the anterior pituitary gland, tells it to secrete our growth hormone, and this can cause our liver to secrete insulin-like growth factors, and together they are going to be synergistic. So they complement one another and they increase the stimulation of cell growth and division, especially of our muscles and bones. Now let's not forget about the posterior pituitary gland. This is also called our neurohypophysis because we have a lot of nerve fibers descending on down here. You could see that the cell bodies are located in the hypothalamus. This is where hormones are going to be produced, and then they move through the axons into the infundibulum and eventually into the posterior pituitary gland, where they are stored until they are needed and they can be released. Now here we don't have a portal system. This is called our hypothalamo-hypophyseal tract because of the axons. And so our hypothalamus, as we said before, is going to create ADH and oxytocin through neurosecretory cells here. What ADH is going to do is decrease our urine production because we're going to reabsorb water in the kidneys. And so it'll stimulate thirst and also constrict our blood vessels. And oxytocin is going to function in uterine contractions, milk ejection, and will help with emotional bonding. I typically call the oxytocin hormone the love hormone. Let's talk about the thyroid gland next. So we have seen this before. We'll see the thyroid gland just inferior to the thyroid cartilage of the larynx. This is also known as the Adam's apple in your neck, and it is found just anterior to the trachea or your windpipe. We have two lobes, a right lobe and a left lobe of our thyroid, and it is connected in the middle in a narrow connection called the isthmus. Now, we can't see any blood vessels in this illustration from your book, but it is richly vascularized, and this is why we get the reddish color to this gland. We'll also see that it's made up of a lot of microscopic follicles, which you could see pictured down over here. This is an illustration on this side, and this is an actual histology slide in which we use stains to kind of highlight some of these areas. So our follicular cells, which are going to be these purple-like round cells here that are cuboidal in nature, and they surround a central lumen, and their job is to synthesize or create a thyroglobulin. This is a precursor for what then becomes the thyroid hormone, also known as T3 and T4. Now, like we said, within this lumen, we are going to have something called a colloid, and this is a viscous protein-rich type of fluid. Surrounding this area, kind of in between these follicular cells, we're going to have parafollicular cells, and these parafollicular cells are going to make that calcitonin. Remember, we talked about that. It is going to help decrease blood calcium levels, and it works in conjunction with the hormone that our parathyroid glands secrete, which is our parathyroid hormone. So just a reminder, those parathyroid glands are found posteriorly on the thyroid gland. So even though it looks like it's sitting anterior here, it is posterior on the thyroid gland. And we usually have 4 of these, but it can range from 2 to 6. These glandular cells are going to contain 2 different groups. We have our chief cells and our oxyphil cells. The chief cells are responsible for making the parathyroid hormone in order to increase blood calcium, whereas our oxyphil cells have an unknown function. Next up, we have our adrenal glands, and these I always like to call the party hats on top of the kidneys. They are going to be retroperitoneal, which means that the parietal peritoneum sits in front of the kidney and the adrenal glands. We also will see that they're embedded in fat and fascia, so sometimes when we're in the lab, we have a difficult time differentiating where the adrenal gland is and where the para and perirenal fat is. But if we were to slice this adrenal gland in half, we would see 2 layers. The inner layer here is known as the adrenal medulla, and it is going to be responsible for releasing epinephrine and norepinephrine when it's stimulated by the sympathetic nervous system for our short-term stress response. And then on the periphery here, we see our adrenal cortex, and this can secrete as many as 25 corticosteroids, and there are 3 different regions. We have the outermost, which is the zona glomerulosa, middle is our zona fasciculata, and the innermost is called our zona reticularis. And next, let's talk about some of the hormones that it is going to secrete. So first off are the mineralocorticoids, and they are going to regulate electrolyte levels. We find that these are synthesized within the zona glomerulosa. And the main mineralocorticoid we need to know of is aldosterone, and that's going to be the one that is going to cause us to reabsorb sodium and allows for potassium excretion. The other hormone that's released, our group of hormones, is the glucocorticoids, and these help to regulate blood sugar, and they're going to come from our zona fasciculata, and they help to release, well, it is itself cortisol that is going to increase blood sugar. And then for our last layer, the zona reticularis, that is going to be responsible for synthesizing sex hormones. And we've got androgens that are going to be released that serve as male sex hormones that can be converted into estrogen in females. These sex hormones are to a lesser extent than they are produced by the testes or the ovaries. And then we've got our pancreas, and this is an elongated organ here that we're going to find between the area of the stomach and the duodenum. In fact, this pancreas, the way it's illustrated, is kind of sitting a little bit low. It actually kind of goes behind the stomach and more at an angle like this here. So we've already mentioned our pancreas is both an endocrine and exocrine gland, and we have special cells that will help us with each function. Our acinar cells are going to do that exocrine function of creating the pancreatic juices for digestion, whereas our pancreatic islets, or islets of Langerhans, are going to have clusters of the endocrine cells. And we give different names to each of these cells because they're responsible for producing different hormones. For instance, the alpha cells secrete glucagon and our beta cells secrete insulin. Next we have our pineal gland, and this is found in the brain. I always search for the thalamus first, which is this egg-shaped structure, and right behind it is the pineal gland. I almost call this like the tail of the thalamus. And this is going to secrete a hormone known as melatonin at night. It causes us to be drowsy and want to go to sleep, and helps to regulate our circadian rhythm and has an effect on mood. We also see that there is a link between melatonin and its influences on our gonadotrophin releasing hormone, which means that it's going to play a role in the onset of puberty. Speaking of puberty, we have to talk about the gonads. So in those that were born with testes, we see them here. They would be within the scrotum, and for ovaries, they would be found in the pelvis. And both of these are going to secrete steroid hormones, meaning they are lipid soluble. Our testes will produce androgens such as testosterone, and this allows for growth and development of the testes, the penis. It increases skeletal and muscular growth, enlarges the larynx so it deepens the voice, increases the growth and redistribution of body hair, especially in the axilla, face, and the pubic region, and will aid in production of sperm cells. Our ovaries are going to produce estradiol and progesterone, and they cause secondary sex characteristics to come about, such as breast development, increase in adipose cells, especially around the hips and underneath the skin, and it prepares the body for childbirth. Some other secondary endocrine functioning organs would be the heart. The heart within the atria are going to be able to secrete atrial natriuretic peptide, and this is a hormone that helps to lower blood pressure. When we have an increase in stretch in the atria, that's telling our heart that it has too high of a blood pressure, and so it starts to secrete this peptide, and the kidneys then increase urine output, which is going to lower our blood volume and in turn lower our blood pressure. It'll also cause the blood vessels to vasodilate, which decreases blood pressure as well. Another endocrine organ or secondary endocrine organ is the kidneys. They are going to release erythropoietin, also known as EPO, and that travels over to the bone marrow and tells it to go through erythropoiesis, or generation of new red blood cells. So typically the kidneys are going to secrete erythropoietin when it senses that we have low blood oxygen. And so by creating more red blood cells, we have more hemoglobin molecules within it that can bind to oxygen and increase our oxygen saturation within our blood. Another organ is the thymus, not to be confused with the thyroid gland. The thymus is a endocrine gland that is going to sit kind of atop and anterior to the heart, and it secretes thymic hormones, which is going to help with the maturation of our T cells, also known as our T lymphocytes, which are white blood cells. Now notice how in a newborn here and through childhood, we're going to see a large thymus, but as we get older, it starts to atrophy and shrink. Lastly, we need to talk about our adipose connective tissue. It serves in endocrine functions because it'll secrete a hormone known as leptin. Now, leptin, when secreted, is going to help control appetite by binding to neurons in the hypothalamus. And we see that lower body fat is associated with less secretion of leptin, and this stimulates appetite. Our adipose has other endocrine effects as well. If we have excess adipose, it's going to raise our risk of cancer. Excess adipose also delays male puberty, and abnormally low adipose is going to interfere with the female menstrual cycle.